Okay. I hope everybody's doing well. Uh, First thing I want to do is talk through some of the way heat is involved in our phase changes. And the other day we went through all the different phase changes, the six of them, right? Freezing and melting, vaporization, condensing, sublimation, and deposition. Right? And we said that heat is required for some of them to occur if we need to speed particles up and separate them. And heat needs to leave some of those to occur if we need to slow particles down so that they can form IFs and create a more condensed phase. So the first scenario I threw at you was this one with oranges in Florida, that when it gets really cold, that they take the orange and they spray it with a layer of H2O if they think the temperature outside is going to freeze. And the whole idea behind that is I asked you what was the phase change in effect and how does it protect the oranges. So most people did a really good job telling me we were looking at a liquid going to a solid, because if it gets below freezing outside, that water is going to turn into ice. The liquid moves faster than the solid does. Right? So whenever that occurs, kinetic energy, heat, needs to leave for those liquid particles to slow down enough for them to get locked in place. And what happens is that heat leaves, sure, it goes out into the cold air, right? But the heat that's leaving as the water freezes also is going to go into the orange. So the orange gets to accept the heat that the water is releasing, and it helps to warm the orange. And then a lot of you went down the path of saying it insulates the orange, which is correct also. Right? So there's two parts to it. Right? The heat entering the orange from the freezing process, and then once you create that little layer right here, it does protect the orange from the external cold temperature. All right, so that was the first scenario and what was happening then. All right, the second one said in the summertime when I am in a swimming pool, right, the pool is say 75 degrees, right, but we went swimming because it's really warm outside. Say we're at 95 degrees. So I'm swimming around in the pool, and then when I get out of the pool, I go from a colder scenario to a hotter scenario, but my body is telling me that I'm getting cold. I begin to shiver, and we're wondering why that is. So what's going on with this one is when you exit the water, you bring water droplets with you. And what happens is those water droplets are going to evaporate. So you have liquid water that's going to turn into a gas. And if the liquid's going to become a gas, we need to speed those particles up so that they can separate. There is going to be heat required to do that. Now, a large amount of the heat is coming from the air around you on the outside, the temperature. But the part that's in contact with your skin on the bottom part is going to take heat from your body. This heat that it needs, it pulls it from your body. So your brain feels heat exiting your body and triggers effects that make you feel cold. So it starts to shiver to try to create more heat to warm you up. You would get goosebumps at times because it will close your pores to stop heat from leaving because they're worried about the body temperature drop. And both of those things occur because the water evaporating off of your skin. So that's what was going on with the second one. Any questions from you guys on those two scenarios? All right, so what I wanted to dive into today was this. I'm saying heat. I'm saying heat. But there is an amount of heat that's necessary for that. And that's what we're going to get into. We're going to talk about the math end of how do we calculate that heat. Right? And that's called heats of fusion and heats of vaporization. All right, so go ahead, take a short song here, and I hope it comes through okay, and copy down what you guys see there about heat of fusion and heat of vaporization. And go ahead, you can copy down example 1, but don't go any further than example 1.
Son of a whore and a Scotsman, dropped in the middle of a forgotten spot in the Caribbean by providence, impoverished and squalor. Grow up to be a hero and a scholar. The $10 founding father without a father got a lot farther by working a lot harder, by being a lot smarter, by being a self-starter. By 14, they placed him in charge of a trading charter. And every day while slaves were being slaughtered and carted away across the waves, he struggled and kept his guard up. Inside, he was longing for something to be a part of. The brother was ready to beg, steal, borrow, or barter. Then a hurricane came, devastation reigned. A man saw his future dripping down the drain. Put a pencil to his temple, connected it to his brain, and he wrote his first refrain, a testament to his pain. The word got around and said this kid is insane, man. Took a book collection just to send him to the mainland. Get your education, don't forget from whence you came, and the world's gonna know your name. What's your name, man? Alexander Hamilton. My name is Alexander Hamilton, and there's a million things I haven't done. Just you wait, just you wait. When he was 10, his father split for the debt-ridden. 2 years later, see Alex and his mother bedridden, half dead, sitting in their own sick, the scent thick. And Alex got better, but his mother went quick. Moving with a cousin committed suicide. Left him with nothing but ruined pride. Something new inside a voice saying, Alex, you gotta think for yourself. He started retreating and reading every treatise on the shelf. There would have been nothing left to do for someone less astute. He would have been dead and destitute without a cent or restitution. Started working for his late mother's landlord, trading sugar cane and rum and all the things he can't afford to sell for. Every book he can get his hands on, living for the future. See him now as he stands on the bow of a ship, headed for a new land. In New York, you can be a new man. New York, you can just do it. New York, you can just do it. New York, you can be a new man. New York, just do it. Alexander Hamilton, Alexander Hamilton. You're waiting in the wings, waiting in the wings. You never got down, you never learned to take your time. Alexander Hamilton, Alexander Hamilton. America sings for you. They know what you overcame, but they know you overcame. Oh, we'll never be the same. Ship is in the harbor now, see if you can spot him. Another immigrant coming up from the bottom. His enemies destroyed his red from Africa for battle. We fought with him, I died for him, I trusted him, I love him. And me, I'm the damn fool that shot him. There's a million things I haven't done. Just you. What's your name, man? Alexander Hamilton.
Okay, so if we're going to talk about figuring out how much energy is associated with these processes, you're going to have to use one of these two values. First one is called the heat of fusion, and fusion is just a fancy word for melting. And the heat of fusion tells you how much energy it costs you to melt 1 mole of any solid at its melting point. So this number value can change, right? This is the heat of fusion of ice. It's water's numeric value for the energy it costs to melt a mole of it. And that number varies because if you think about it, if we have our ice cube, and let's say we have a mole of it, there's certain intermolecular forces that hold that solid together that we need to overcome. For water, it's a hydrogen bond and it's London dispersion forces. Right? But the stronger these connections get, the higher this numeric value goes. So if I have a much stronger connection here, like a metallic bond, if I'm trying to melt copper, for instance, this number is substantially higher. So just understand these two numbers are specific to water for the examples I'm doing. I could easily give you the heat of fusion of something else, and I would just tell you what that number is. All right, so the heat of fusion is how much energy it takes to melt a substance, to take it from this to basically looking like this. Heat of vaporization is how much energy it takes to separate all of these guys and give them enough energy to escape the container that they're in. All right, and that's why there's more energy required, right? It's tougher to make a substance turn into a gas than it is to melt it. And the kilojoule number you get will correspond to a temperature, but we're going to keep it simple for now. We're just going to work with the thing in kilojoules, our energy unit. So if I wanted to solve these, this is a bracket problem, which we've done a lot of. And the key to all of our bracket problems is we try to get ourselves to moles as quickly as we can. Because if we do, once we're in moles of a substance, we can pretty much convert it to anything else we want. So if I look at this first example that says how much energy is needed to melt 47.0 grams of ice, right? I'm trying to get energy, and my unit of energy is kilojoules. So I'm going to start with what I'm given, which is the 47.0 grams of water. Just like always, I'm going to convert this thing into moles. Not a mole to mole ratio, so 1 with moles. Gram number comes from the periodic table. I take 2 H's, which are 1.008, plus the 16.00 for the oxygen, and you're going to get the 18.02 grams. So now we got ourselves to moles of the substance we're working on, and now we want to see how much energy it's going to take to change its phase. So we're going to do moles on the bottom, and we're going to go kilojoules on top. And here's where you have to pay attention to what the phase change is, because this kilojoule number is going to change based on what the substance is, water, and based on what we're doing to it. So as I look into the question, I am melting, which means I'm looking at the heat of fusion, and it's ice, which means I can use the 6.009 kilojoule value, right, for this guy. Right? So we convert our moles into kilojoules. If we do that, you're going to end up getting 15.7 kilojoules of heat needed to make that ice cube melt. And so if we start in grams, we can convert to moles, and you can use this value or this value to get to kilojoules. All right, take a second, copy down example 2. All right, and we'll solve that one in red underneath it. All right, so number 2 wants to know how much energy is needed, this time to vaporize 184 grams of water. All right, so we're starting out the same. Start with what you're given. And this time, we're going to get it some moles. Hasn't changed. We're still working with water, so our first step's going to look the same. Grams on the bottom, 1 mole on the top. Periodic table number for this guy. All right. Now we want to convert our moles of water into kilojoules. And again, this is where you have to be careful. Who are we working with? It's water. And what are we doing phase change Y is going to dictate the number. So it's still water, which means these two numbers are fair game. But this time I'm vaporizing it, so I need to use the 79 value. And that was all because I was vaporizing in the red and I was melting in the black. You do your math on this one. You're going to get 106. Actually, let me run the math on that because we get 4 sig figs. So 184.0 divided by 18.02 times the 40.79. Oh, sorry. I had a different answer set up from something a long time ago. All right, so this value with 4 sig figs is going to be 416.5 kilojoules. All right, and that number is different for a variety of reasons, right? The first reason it's different, it's a different phase change. So it's harder to boil water than it is to melt it. And then secondly, we had a lot more water. In the second example, right, I had about 4 times as much water, right, as I did in the first one. So that by itself would have made me have to expend a lot more energy to melt the bigger sample. All right, so those are 2 styles of problems you'll see. One using vaporization, one using that fusion number, which is melting. All right, number 3 and 4 show you the other 2 things we can do. So take a second, copy down example 3. Example 3. How much ice can be melted if there is 286.2 kilojoules of heat energy available. So how does this question become relevant? Well, you know how in the winter when we freeze things over, whether it's an ice skating rink, whether it's a lake, a pond, something like that, sometimes we get above freezing, but the lake doesn't thaw. The ice rink doesn't thaw. All right. And a lot of people wonder, well, why is that? Well, the temperature that we get from the sun has a certain amount of energy packed in it based on how big that number is. Well, sometimes that energy that's available to us based on the temperature, right, isn't enough to melt the entirety of the sample. It's always going to melt some of it, but it might not be enough to melt all of it. So this is how they kind of know if you're going to have to be safe or unsafe if you want to go ice fishing or something like that. Right now, the setup for us isn't much different. We have to start with what we're given, which is the 286.2 kilojoules. And just like always, I want to get that into moles, right? The key for us is to get to moles as quickly as we can. So I need to get rid of the kilojoules and get that into moles. And who it is important, and what we're doing to it is important whenever we do kilojoules and moles in the same step. So we're still working with water, right? I themed it for these first three that we had water as our substance. The kilojoule number is based on what we're doing. So I have to read and see how much ice can be. Because I'm melting, I know I need to jump up here and use the heat of fusion, the heat of melting number. So I'm going to use the 6.009 value there. So I just got myself into moles. And because it said how much, you'd be okay stopping right there. Now I'll go the extra step, right, just to show you how to get it to grams if we needed to, right? But we'll do it both ways. I'll take my 286.2 divided by 6.009. Right? And this is saying I'd have the ability to melt 47.63 moles of ice. And you're going to say, wow, that sounds like a lot, right? Like 47 moles, that sounds like a pretty big number. So let's take a look to see what that 47 is really worth. So if we convert the 47.63 moles of the ice into grams, and you could do this right here if you wanted to. And I just broke it into two steps so you could see it. We would convert the moles into grams by putting moles on the bottom, grams on top. It's still water, so it's H2O, and that's why I added up the two H's and the O from the table. And if I take my 47.63 times the 18.02, all right, that's telling me that I can melt 858.3 grams of water. And you're going to find out that is not very much. 800 grams of water is only about 2 pounds of water. So even though that mole number looked big, if we were talking about trying to thaw an entire lake, right, it wouldn't even make a dent. This day must have been just above, all right, 32 degrees. And we were only able to melt a very, very tiny bit of the water on the lake. All right, so that's how you would do one if they start you with kilojoules and you have to get to an amount, whether it's in moles or whether they ask you to get all the way to mass, right? You would have to do the two brackets to get it to grams. All right, the last one I want to show you is how do we do this thing if they ask us for what this number should be? What is the heat of fusion? What is the heat of vaporization? So take a second and copy down number 4. So number 4, determine the molar heat of vaporization of ethanol. And I told you ethanol's formula because you wouldn't know that one. If it takes 42.78 kilojoules of heat to boil a 42.50 gram sample. So if they ask you to find the molar heat of something, whether it's fusion or vaporization, what you are trying to get is the kilojoules per mole. So these ones here aren't hard because there are all these brackets. They're tricky because they're overly simple, and that's what trips you guys up sometimes. So if I need to find the molar heat of vaporization, I just need to get the kilojoules of energy divided by the moles of the substance. So if I look at my question, right, the kilojoules of energy they gave us, they told us it was 42.78 kilojoules of energy that was needed. So I'm halfway home. What I need to do is divide that by the moles of the substance, right? And that's going to require a little bit of work because they gave me grams of the substance. We have 42.5 grams of the C2H5OH. So we're going to have to convert that into moles. And as long as I tell you who the substance is, all you do is go to the periodic table to get what you're looking for. All right, so I go to the periodic table. I'm taking 2 carbons, 2 times 12.01, plus 6 hydrogens, because there's that H at the end, 6 times 1.008, plus the oxygen, which is 16. So we get 46.07 grams there. Do my division, 42.50. Sorry, I dropped a sig fig on there for you. Divided by 46.07. And we get that there are 0.9225 moles of the ethanol. So to boil 0.9225 moles of ethanol, it cost us 42.78 kilojoules. So I just bring this guy up here. And I'm just taking the kilojoules divided by the moles. So my 42.78 divided by 0.9225. Okay. And ethanol's heat of vaporization is going to be 46.37 kilojoules per mole. All right, so that's how you would get the number value. If I get asked for the heat of vaporization or the heat of fusion for a substance, all I do is take the kilojoule number that they'll give you, and you have to divide it by the moles of the substance that was there, and you get the kilojoules per mole. Now, that number means something, right? The fact that that number is higher than water's number indicates to me that the ethanol has stronger intermolecular forces than that, but we're not even going down that road. Today's theme is all about just the math end. How do I generate the math numbers? Questions on any of that from you guys? All right, so while you're here, I might as well just tell it to you, but I will also send this out in a parent square. Just some practice problems coming your way. All right, so page 386. Practice problems numbers 1 and 2, and I'll send those pictures. And then later on, 389. All right, number 27 to 31. All All right, now send the picture of those out as soon as we get off. The video, if it uploads quickly, I'll upload the video as well. So if you had a friend that couldn't make it, you can share that with them. But if the video isn't uploading fast, I'll send you guys the homework so you can do it while you're fresh in your mind. And I'll upload the video as soon as I get it up onto YouTube. Hope everybody is doing well. Any questions before we break huddle from you guys today?